Okay, chapters 13 and 14, I kind of mixed them together in these notes. So this video is going to cover both of those chapters. And as you're doing your homework, you'll see why. As we go through this, you'll see why as well, why they're mixed together. 13 and 14, it's going to be pretty different than what we have been covering. We're going to be doing a lot of math with this. It's probability and chance, and most of what we see here will be stuff you've covered before. In secondary math 2, you did cover probability unit, so hopefully a lot of this is familiar to you. Okay, so probability was developed to solve gambling problems. That's really where it started, was with gambling. A chance can be written, so a chance or a probability can be written as a percent. So let's say like 50%. As a fraction, so 50% is 1/2. As a decimal, so 50% is 0.5. So there's those three. You can write it as a sentence as well. So if you know what you're talking about specifically, you can say the chance a coin lands on heads is 50%, or lands on 6 for a dice or a die, and so on. So chance and probability, they're one and the same. The chance or probability, you can say it either way. With those, we've got some vocab words. So the first is event. Event is what we want to happen. So let's say you flip a coin and you want it to land on heads. The event is getting heads. If I want to know the probability of getting heads, this is how you write it as a sentence. As a mathematical sentence or statement, you can write it like this. The P stands for probability of getting heads. And we know if you flip a coin, you have a half a chance of getting heads. So it's 1/2 or 0.5 or 50%. Or in other words, we expect 50% of the time we'll get heads. To get that 50%, I mean, with a coin, that's pretty obvious. But there's a formula we can use. The probability, so remember that P stands for probability, of getting some event. Do not read this as probability times event. I know the parentheses can be confusing there and make you think probability times something, but it's not saying multiply. It's just a fancy way of saying the probability of some event is equal to the number of times it can happen, so the number of successes over the total possibilities. So you can get heads on a coin one time out of a total of 2 options. And this bottom, the number of successes and failures, that's also called the number of outcomes. That's how many possible outcomes you can get. So if you're flipping a coin, or rolling a die, your options are 1, 2, 3, 4, 5, 6. So if you want an odd number, the probability of getting an odd is equal to 1, 2, 3. And there's 3 options that are what we want out of a total of 1, 2, 3, 4, 5, 6 options. So probability of the event is equal to the number of successes, or number of times you can get what you want, over the total number of options. So we know when you flip a coin, there's 2 options, heads or tails. Probability of getting heads was 1/2. Probability of getting tails was 1/2. Rolling a die, oh, we just did this. Rolling an odd number. Well, there's 1, 2, 3 odd numbers out of a total of 1, 2, 3, 4, 5, 6 options. So 3/6. You do not have to simplify that down unless you want to. If you flip 2 coins, when you flip those 2 coins, each coin has 2 options. So the first coin can get heads, and the second coin can get a head or a tail. Or the first coin could get tail, and the second coin could get head or tail. So we have 4 total outcomes here. And with flipping coins, it helps to write out the options. When we flip, we want to know the probability of flipping at least one head. Well, looking at this, there's this one that has at least one heads in it, this one, and this one. So 3 of the total 4 possibilities. Note that the numbers, the probabilities or chances we always write will be between 0 and 100% or between 0 and 1. You can't have more than 100% or less than 0%. If 2 events are opposite, then the probability of an event happening is equal to 1 or 100% minus the probability of the opposite event. So flipping a coin, you can either get heads or tails. Those are the only 2 possibilities. So these events are opposite of each other. So the probability of getting heads is 1/2, which means the probability of getting tails is equal to 100% or 1 minus the probability of getting heads, or 1 minus 1/2, which is 1/2. Okay, that one, of course, the probability of getting tails is 1/2. This work right here is more confusing than just saying, yeah, we know it's 1/2. So let's look at it where it might be a little more useful. Probability of, let's skip this one, rolling at least 2. Okay, at least 2 means you get a 2, 3, 4, 5, or 6. So when we write it out like that, we can see it's a 5 out of 6. But the opposite event of at least 2 is getting a 1. Or getting less than 2, which is only a 1 if you roll a die. And the probability of getting a 1 is 1 out of 6. Notice 5 out of 6 and 1 out of 6 does add up to 100%. So another way to do this, rather than writing out the possibilities and counting how many there are, you can just say, well, what's the opposite of that? Getting 1, there's only 1 option out of 6 total. So if I do 1 minus that, that will give me the opposite events. That will give me the 5 out of 6 other options that I'm looking at. So if I want at least 4, the opposite of at least 4 is less than 4. So opposite is less than 4, which means 1, 2, 3. So we can do, it's equal to 1 minus the probability of the opposite, which is equal to 1 minus 1, 2, 3, 1/3, which is 1/3. Okay, again, that one's not super useful. Probability of rolling at most a 5. And that's saying 1, 2, 3, 4, or 5. So the opposite event is more than a 5. Well, the only way to get more than a 5 is to get a 6, which only has a 1/6 chance of happening. So rolling at most a 5 is equal to 1 minus that 1/6 chance of not rolling at most a 5. So it's 5/6. Okay, all of these that we just went through here, you can just do that without doing this 1 minus thing. But if you're given 100 different outcomes, it might be more beneficial to do the opposite event. And I'm going to write something else with that. Okay, so with this formula right here is going to be pretty useful. Anytime you see the word at least or the phrase at least, it means do 1 minus opposite. I should say 1 minus the probability of opposite. And we'll go through that again. But this is what you need to get from that. Okay, so when you flip 2 coins, these are your 4 possible outcomes. The first coin can land on heads, second coin can land on heads. First coin can land on heads, second coin can land on tails. First coin can land on tails, second coin can land on heads. First coin can land on tails, second coin can land on tails. So I want to know the probability of rolling at least one head. Well, the opposite of that is rolling no heads. So more than just the probability of rolling at least equals 1 minus the opposite, we can take that further and say when you see the probability of at least one of something, it's equal to 1 minus the probability of none. And this is going to be used quite a bit. So rolling at least one head, that's going to be equal to 1 minus the probability of no heads. Well, there's only one option that has no heads, so it's 1 minus that 1 out of 4 options, which leaves us 1 minus 1/4 is 3/4. And I know you also could have just counted that 1, 2, 3. You can do it either way. Opposite of rolling no heads is rolling at least one head. Actually, you know what? I'm not going to do that one. That's not beneficial to us at all. Probability of rolling all tails. Let's not worry about the opposite event. All tails is just that. And there's 1 out of 4 options. Okay, the difference between drawing with or without replacement is the next thing we're going to talk about. So if you've got a box and inside that box you have 3 different cards or 3 different tickets. First ticket has a 1 on it, second ticket has a 2, third ticket has a 3. So suppose you draw a 3 first. And then you stick it back in so the box looks the same after that first draw. So your second draw, you're able to choose 3 different cards. So you have 3 possible outcomes for that second draw. But let's say you do it without replacement. You don't stick that 3 back in. Then the second draw, you only have 2 possible outcomes. So that changes the denominator of your fraction. This one would be over 3. This would be over 2. So we've got this difference between with and without, and that's important to know which is which. That was all there, yeah. Okay, let's say we draw 1 ticket out of a box, and we want to know the probability of drawing a B. The opposite of that is not drawing a B. And we don't actually have this box here, so all we can say is it's equal to 1 minus the probability of not a B. Now let's say we draw 2 tickets out of a box. So this is for 1 single ticket. Now we're drawing 2 tickets out of a box. We're going to get different options. You can draw it with replacement or without replacement. With replacement, after the first draw, the ticket is placed back in the box, and it's like the box has no memory that the first ticket was drawn. So if I draw 3 out the first time and then stick it back in, the box doesn't remember which card was pulled out, so it's just as high of a chance of getting a 3 as it is a 1 or a 2. Versus with replacement, you can't draw that 3 again without replacement, you can't draw that same number again because that's no longer an option. And you'll see that written as given that some event occurs. So given that we've already pulled out a 3, what's the probability of pulling out a 2 second? So let's look at a couple examples. We draw 2 tickets out of a box with replacement. So let's say this box has an A and a B in it. What's the probability of drawing a B given A was drawn first? Well, I don't even care what was drawn first because it's with replacement. So the probability of drawing a B is 1/2. because there's 2 cards in the box. I don't care what happened the first time because it's back in the box, so it can be drawn again. Versus if I draw it without replacement, so let's say we've got our A and our B. Sorry, that's super small. Maybe I need to rewrite that. Okay, so without replacement, I want to know the probability that on the second draw, I get a B, given on the first draw, I got an A. Well, I haven't put that A back in. There's only 2 cards there, so it's a 1 out of 1 chance, or 100% chance. So that's the difference between with replacement versus without replacement. This without replacement thing is a conditional probability. Anytime you see the word given, that means conditioned or conditional probability. It's on the condition that something happened. So if I roll 2 dice, I want to know the probability of getting an ace, and ace just means a 1 on that first dice and a 1 on the second dice. So here it says getting an ace given an ace was rolled first. Well, I'm rolling 2 die. The first one got a 1, then I roll the second die. I want to know the probability the second one got a 1. What happens with this first die has nothing to do with what happens on the second die. So we don't really care what happened with the first die. The probability of getting a 1 on the second die is just 1/6. There's 1 sign that has a 1 on it out of a total of 6 options. Okay. Versus this next one. Oh, it's the same thing. So rolling a die and tossing a coin, getting an ace, so a 1 on the die, given a heads was tossed. The die doesn't care what the coin did. So we've got the head on this one. There's, that doesn't look a thing like a head. Well, that didn't work so well. We've got this die that doesn't care what the coin did, so I don't care what happened here. There's still just a 1/6 chance. Knowing one event occurred, but it does not change the probability of another event occurring, means that the 2 events are independent. So the way I think of the word independent is if you're living with your parents, relying on them for food and shelter, you are dependent on your parents. Versus when you move out, you don't ask them for food or for money or for shelter. You are independent of your parents. You're taking care of yourself. In probability, these 2 events we just looked at are independent because the second event doesn't care what the first event did. It's independent of that first event. So if I'm rolling a die and flipping a coin, the coin doesn't care what the die did, so it's independent. They're independent events. Or if you have a box with something in it and you draw with replacement, it doesn't matter what happened on that first draw, so it's independent of the first draw when you do the second draw. Okay, so drawing from a 52 card deck. I know some of you are not aware of what happens or what's in a 52 card deck. If you don't know, let me just give you a quick summary. In a 52 card deck, there's 4 different suits. So we have hearts, diamonds, spades, and clubs. In each suit, there's 13 cards. So there's 13 hearts, 13 diamonds, 13 spades, and 13 clubs. Hearts and diamonds are red. Spades and clubs are black. This makes a total of 52 cards in the deck. So we've got to find probability for some of these events. I want to know the probability of drawing 1 card from a 52 card deck. Specifically, I want that card to be an ace. Well, in each of these 13 suits, these are the cards available, and this happens in each of these different suits. So if I want an ace, an ace can happen in the hearts, diamonds, spades, or clubs. That makes a total of 4 options out of the 52 options. If you want to simplify that, you can. You don't need to. Drawing a red card, well, there's 13 reds and 13 reds. That makes a total of 26 out of 52. Again, if you want to simplify it, you can. Drawing spades, well, there's 13 spades out of 52 options. If you are not familiar with cards, I would recommend writing this down with face cards. Writing this down, if you need to look into it a bit more, you can. Just make sure you get familiar with face cards because you will need to know these different numbers for how many different suits there are and that kind of stuff. Okay, so that's if you're drawing just one card from the 52 card deck. Now let's say you draw 2 cards and you're doing it without replacement. So I want to know the probability that the first card is an ace. We just did that, 4 out of 52. Now I want to know the probability the second card is a jack. This doesn't tell us the first. So because it doesn't tell us anything about the first draw, we can't make any assumptions about that first draw. So because we don't know what happened with the first draw, we can't discount that one draw that was made. So there's still 52 options because we don't know what that first option was. And there are 4 jacks. I kind of hate this problem, but I see it show up every once in a while. I don't care too much about it. I won't ever put it on a quiz or a test. And if I see that it's on the final, I'll prepare you for that. So don't worry too much about this. But if you understood what I just said, that's great. Okay, this is where we're going to take into account what happens with the first card. So we want the probability that the second card is a jack, given that the first card is an ace. So we already know that the first card is an ace, so we only have 51 cards left in the deck, and I know there's 4 jacks. Then I'm drawing again, so this is a new draw. The first card was a heart, so now there's only 51 cards left in the deck, and I want to know the probability of getting another heart. So there were 13 hearts, but I drew one of those out. So now there's only 12 hearts and only 51 cards. We can do it with replacement. The probability of drawing a heart, given the first was a heart, well, that first was a heart, but it was put back in, so I don't care what happened with that first draw. The probability of drawing a heart is 13 out of 52. Sorry, just counting how many more pages of this we have. Okay. Whoop. Okay, 2 things are independent if the chances for the second are the same no matter how the first turns out. Okay, we already talked about this idea of independent. A coin and a die are independent of each other. What happens with the coin has nothing to do with what happens with the die. If you roll or flip 2 coins, they're independent. If you flip a coin and then flip the coin the second time, that second coin toss has nothing to do with the first coin toss. So here's just some examples that we've already talked about. If you're not replacing in the box, they no longer are independent because that denominator has changed. But if the denominator doesn't change, they're independent. Okay, if 2 events are independent, you're going to see the word and for independent events, and that means multiply. So the word and means multiply the fractions together, or the 2 probabilities together. The probability that 2 events will both occur equals the probability of the first event multiplied by the probability of the second event. So this is when events are independent. What happens on the first event has nothing to do with what happens on the second event, like rolling a die and flipping a coin. They're independent of each other. Or when you do things that are with replacement, you just multiply the two probabilities together. So I want to know the probability of drawing an ace and a jack. Well, for an ace, and it is with replacement, so it is independent. For an ace, the probability is 4 out of 52. There's 4 aces in the 52 cards. Then we stick whatever card it was back in. Now we have a 4 out of 52 chance of drawing a jack. Multiply them together. You don't even have to do that multiplication. Just write it like that, and that's good enough. Okay, rolling a die and tossing a coin. Yes, those are independent. So we checked for independence. As long as they are independent and you see the word and means multiply, you can just remember that. If you see the word and, you're more than likely going to be multiplying. The only case where that's not true is if they're not independent. You won't see that very often. So if we roll a 6, that's a 1/6 chance of happening on a die. Getting a coin is a 1/2 chance of happening on a, getting a tails is a 1/2 chance of happening on a coin. So it's that. And again, you do not have to simplify that down. If you want to, you can. I'm not going to. It's just 1/6 times 1/2. Okay, dependent events can happen or can use the multiplication rule. I'm not going to take the time to go through this because you won't see it. It's more complicated than we need to worry about. So don't worry about this slide. That just what happens if you draw like without replacement and you're looking for 2 possibilities. Actually, I guess we can do this because it's pretty obvious. So without replacement, getting an ace, there is a 4 out of 52 chance of that happening. And then a jack, there's a 4 out of 51 chance of that happening because they are not dependent. They are not independent, so 1 card's already been pulled out. That's all you need to know about that. Okay, I'm going to skip this slide. I don't think it's too important. If the chance of having a boy is 1/2, like flipping a coin and getting heads, and a couple plans to have 6 children, the chance they are all boys is 1 out of 64. What is the chance of them having all girls? Okay, so we're just saying genetics doesn't play into this at all. We're just saying that there's a 1/2 chance of the baby being a boy, 1/2 chance of the baby being a girl. Let's look at this 1 out of 64 first. So for the probability of the baby being a boy, we have 6 babies. So baby 1, baby 2, baby 3, baby 4, baby 5, and baby 6. There's a 1/2 chance of the first baby being a boy, 1/2 chance of the second baby being a boy, 1/2 boy, 1/2 boy, 1/2 boy, 1/2 boy. This is independent. The second baby's gender is independent of the first baby's gender. There's no memory, is how you can think of it, of what the first baby is, so it's not going to make an influence on what the second baby is. Since it's independent, it means and as I just explained it, I said the first baby and the second baby and the third baby and the fourth and the fifth and the sixth. The only other option would be to say or, and that doesn't work because we're talking about all of them, not one or the other. So because it's and, it means multiply. So we just do 1/2 times 1/2 times 1/2 times 1/2 times 1/2, 2 times 2 times 2 times 2. Yeah, that's 1 out of 64. That's where that comes from. Okay, that's this number. Now we've got this chance of it being of all girls. Well, the probability of the first baby being a girl is 1/2. Second is a girl, 1/2. Third is a girl, 1/2. Whoops. 1/2, 1/2, and 1/2. So guess what? The probability of them being all girls is the exact same thing. If the chance of having a boy is 50% and a couple plan to have 6 children, the chance they have 6 boys is 1 out of 64. What is the chance of them having at least 1 girl? Okay, this is where one of our formulas comes in. I said probability of at least 1 is equal to 1 minus the probability of none. Well, at least 1 girl would mean opposite of that is no girls, which means all boys. So we already know the probability of none, or the probability of all boys. It's 1 out of 64. So the probability of at least 1 girl is 1 out of 64. Which is 63 out of 64. Okay, another question. A child has 4 Easter eggs, 2 pink ones, and 2 blue ones. If the child chooses 2 eggs at random to eat, what is the chance they are both pink? Okay, so we have 2 pink eggs. Let me choose a pink color. Here's my pink egg. That doesn't look a thing like an egg. Whoops. And 2 blue eggs. I want to know the probability. Okay. If a child chooses 2 eggs at random, what is the chance they are both pink? So this is without replacement because she's choosing both of them. She's not choosing one and then sticking it back in. So the probability of them being both pink would not just be 1/2. You'd have to go through quite a bit of work to figure this out. Actually, let's just think of it this way. Probability of the first pink or the second being pink given the first is pink. I was going to have us write out all the options, but I think this will be easier. So the probability of the second being pink given that the first is pink. Well, the first is pink is a 2/4 chance of happening. The second being pink, well, we've already pulled out one of them. So that's a 1/3 chance of that happening. And both of them have to happen. First is pink, second is pink. Since they both have to happen, it's first and second, means multiply. That is 2 out of 12, which is 1/6. Another option would be to go through and write all your possibilities out. Pink, 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 blue, pink. Oh, I guess there's also another pink, pink option. Pink, blue, 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 pink, and so on. You'll get 12 options there somehow, and you'll see 2 of them are pink, pink. So you've got 2 options to do that one. Main thing you need to know from this is it was without replacement, but you would multiply. Okay, when you have a bunch of outcomes, you can list them out like I was just doing with the eggs here, listing out the different possibilities, pink, 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 blue, and so on. And the most beneficial time to do that is when you're rolling a die. So if you're rolling 2 die, let's just stick with 2 die here, you can list all the possibilities out, and you see there's 36 different possibilities. There's some other options listed here, but the die is the one I care about. So the first die, let's say you're rolling a white die and a black die. First die can be 1. Second die can be 1 through 6. First die can be 1 through 6. There's 36 possibilities here. That's what's important to know. Each of the 36 possibilities has a 1 out of 36 chance of happening. So let's say I want to know the chance of rolling a 7. Well, let's just look. What it's saying is the sum of the 2 die is 7. So the total number of spots is 7. So looking at this, I'm just looking for any 2 die that add up to 7. 6 and 1 adds to 7. 5 and 2, 3 and 4, 3 and 4, 2 and 5, 1 and 6. So there are 1, 2, 3, 4, 5, 6 out of the 36 options to get to that 7. So we just said the probability of rolling a sum of 7 is 6 out of 36. This leads us into not 6 out of 37, 6 out of 36. This leads us into what's called mutually exclusive events. So we have independent events, and that means and, where you multiply. Mutually exclusive events are events that cannot occur at the same time. So you cannot reach into your drawer and pull out a blue pair of socks and a red pair of socks if you're only pulling out one pair of socks. You cannot do both at the same time. That's mutually exclusive. Or you cannot be in New York and Utah at the same time. The probability of being in New York is mutually exclusive from the probability of being in Utah. So when you have mutually exclusive events, you're going to use the word or, the probability of being in New York or being in Utah, because saying and doesn't work there. And when you see the word or, it means add. So we have 3 main things from these 2 chapters. At least one, the probability of at least one means 1 minus the probability of none, and means multiply, or means add. And then we also have the definition for independent and mutually exclusive. So at the end of this, I'll just summarize those things. That's what's important for this. Okay, so if events are mutually exclusive, when you see the word or, you just add the probability of the 2 different events happening. So here's some examples. If you toss a coin, you cannot get a heads and a tails at the same time. If you roll a die, you cannot get a 6 and an odd number at the same time. But note that 6 and even numbers are not mutually exclusive because 6 is an even number. And there's a few other options there. Okay, so we already know the probability of rolling a sum of 7 is 6 out of 36. Now I want to know rolling a sum of 7 or rolling a sum of 11. So let's go back a couple slides and look at our die options. Okay, we have the 7 is 6 out of 36, or you can simplify that to 1/6 if you want. A sum of 11 only happens 2 different ways, 5 and 6, 6 and 5. So that's a 2 out of 36 options. So we have 6 out of 36 or 2 out of 36. So to get a 7 or an 11, we have 6 options plus another 2 options. Makes a total of 8 out of 36 options. And you can go back and count that if you want. We circled 6 in green, 2 in blue, so there were a total of 8. Rolling a 1 on the first die or rolling a 3 on the second die. So let's go through and look at all of our... Actually, I don't like that one. Let me show you why I don't like that one. So we're going to go count all of our options for a 1 on the first die or a 3 on the second die. 1 on the first die, 3 on the second die. These are not mutually exclusive because my blue and my green happen at the same time. So it's possible to roll a 1 on the first die and a 3 on the second die, so they're not mutually exclusive. So you can calculate the probability of that, but that's more complicated than we're going to do in this class. So we just write not mutually exclusive, since they can happen at the same time. So we're not going to calculate that. With decks, so let's say we're drawing without replacement. Drawing an ace has a 4 out of 52 chance. Drawing a jack has a 4 out of 52 chance. So there's the word or means and. There's 8 ways to draw an ace or a jack. But if I want to draw an ace or a heart, there is an ace of hearts. So this is not mutually exclusive. So we don't worry about it. Okay, toss a fair coin twice. What is the chance of getting one head or one tail? I don't care about that problem. Okay, if you want to watch this, you can. This is Peyton Manning and Magic Johnson playing egg Russian roulette. They're just breaking eggs over their head. 4 of them are raw, 8 of them are hard-boiled. And you can just go through and see the probability of each of these. I'm not going to take the time to do this, so I think you'll get plenty of practice with your homework on this, but if you want to watch it, it's a cool video to watch. And you can answer these questions if you want to. Okay, a couple more questions. 3 dice will be rolled. What is the chance that they all show 1? Well, there's only one possibility for all 3 of them to show 1. I don't like this problem either. It's more complicated than it needs to be. So it's the probability that the first one shows 1 and the second one shows 1 and the third one shows 1. So it's an and. The probability of a 1 is 1 out of 6. Probability of 1 is 1 out of 6. 1 out of 6, so it's multiplied. If you understand it, that's great, but that's a little more complicated than I would ask. Okay, let's go through this just a little bit. I want to show you where probability first started. So there's 2 games. The first game, you roll 4 die, and you win if at least 1 die shows a 1. Sorry, the wording is off just a little bit here. This die should be here. So if 1 die shows a 1, you win money. This game, you roll 2 pair of die, or 2 die. 24 pairs of dice is what I should say. And you win if you get snake eyes. And this guy said in game 1, you have a 2/3 chance of winning, and in game 2, you have a 2/3 chance of winning. So there's equal chance of winning. So you should play the one that pays off more money. But everyone knew by experience that game 1 was more likely to be won than game 2. So let's look at where his error is. He said you can get a 1 on the first die, or on the second die, or on the third die, or on the fourth die. So there's 2/3 chance. What he didn't account for was getting a 1 on the first die and second die, or a 1 on the second die and the fourth die, or all those possibilities of getting 2 1s, 3 1s, 4 1s. And he made a similar mistake here, getting a 1 on the first pair, a 1 on the second pair, and so on, but he didn't take into account the chance of getting more than 1 pair. So these 2 men are mathematicians. You probably don't know Fermat. He's known for Fermat's last theorem. That's his main thing. Pascal, you know about Pascal from Pascal's triangle that you'd studied in Math 3. They got together and said, look, man, this guy, what's his name? Chevalier de Meyer? I have no idea if I said that right. They said, look, you did this wrong. Let's show us how it's supposed to be done. So in game 1, you want at least 1, 1. Well, we said the probability of at least 1 is equal to the probability of, is equal to 1 minus the probability of none. So, since you forgot to count all those duplicates, we're going to do it this easy way and do 1 minus no 1 on the first roll, or on the first die, no 1 on the second die, no 1 on the third die, and no 1 on the fourth die. That gives us this probability. You have over 50% chance of happening. Versus the second one, we're looking at the probability of at least 1 snake eye is equal to 1 minus the probability of none, or no snake eyes happening, which has a 35 out of 36 chance of happening on all 24 pairs. This should be raised to the 24th power, so that's equal to just under 50%. So we've got that problem there where Chevier, or whatever his name is, forgot to count those duplicates. Pascal and Fermat said, oh look, it's easier to calculate if you do it this way, to count all those duplicates by just using our formula. The probability of at least 1 equals the probability, or 1 minus the probability of none. So then we've got this question. If you roll 2 fair die, what's the probability of at least one of them showing a 1? Well, probability of at least 1 is equal to 1 minus the probability of no ones. So on the first die, we don't want a 1. On the second die, we don't want a 1. So on the first die and second die, there's no 1. There's our and, means multiply. And it's 1 minus this probability. So 1 minus 25 out of 36 makes 11 out of 36. And I think that's all we need to go through. The rest of these slides I'm going to skip. We've covered what we need to for this. So you're good to work on the homework. Let me know if you have questions. I know we covered a lot of stuff on that. Let me just do one quick thing here where we just summarize what we talked about, the important points from this. First, probability of, that is a very thick pen. Probability of at least 1 of whatever the event is equal to 1 minus the probability of none. And means multiply the probabilities together, or means add the probabilities. Independent means first event is not affected by the second event or has no influence on the other event, so the two events have no influence on each other. Like rolling a die and flipping a coin. And mutually exclusive means cannot happen at the same time. You cannot draw one card out of a deck and get both an ace and a jack. So that's mutually exclusive. That's really the main points from this chapter. Probability can be confusing if you overthink it. So be careful and don't overthink it. If you do start getting super confused, just walk away from it for a few minutes and then come back to it. Just don't overthink it. Use these basic 3 things to help you out there. Speak it out loud. If you were to say the probability of this or this, add. If you're saying the probability of this and this, multiply. And then your homework is this. No, it's not. We shorten the homework. Let me see real quick. I need to pull it up. So we did shorten the homework. And this video does get you ready for both chapter 13 and 14 homework, hopefully. So 13 and 14 homework are due Friday, April 17th. Chapter 13, you're doing set A, just numbers 1 through 3. All of B, set C, you're just doing 1 through 2. Set D, you're doing 1 through 4. And review, you're doing 2, 3, and 6. Chapter 14, doing all of set A. Set B, you're just doing number 1. Set C is gone. Set D, you're doing 1 through 5. And review, you're doing 1 and 5 through